Okay, let us start again. Now suppose phi 1, phi 2, etc. phi n are n functions which is continuous together with their n minus 1 derivatives over the interval t1 to t2. So you take phi 1, phi n, phi I, t1, t2, and suppose equal to 0. Now we know that one cannot say, so this does not imply that phi 1, phi 2, etc. phi n are linearly dependent. We have seen examples for that. However, what one can say is a partial result, namely that there exists a subinterval of on which so universally on this interval you cannot say that the function is linearly dependent, but there is some subinterval on which the function is linearly dependent. See, so what all things we have proved? Let us recall. If phi 1, phi 2, etc. phi n are solutions of a homogeneous equation, okay, and w of phi 1, phi 2, phi n is identically equal to 0, then phi 1, phi 2, phi n are linearly dependent. Or, sorry, the other way. Yeah. Yeah, that's right. This is if and only if they are, of course, the solutions of the equation, then phi 1, phi 2, phi n are linearly dependent if and only if w of f phi 1, phi 2, phi n is equal to 0, or equivalently phi 1, phi 2, phi n are linearly independent if and only if the Wronskian is not vanishing on the whole interval. I mean nowhere on the interval. But suppose we drop that criteria, namely phi 1, phi 2, phi n are solutions of the equation. Then what we can say is that phi 1, phi 2, phi n are linearly dependent implies the Wronskian is identically equal to 0. But the converse is not true. We have already seen an example. What you can say is that, so the converse is this: if w phi 1, phi 2, phi n is identically equal to 0, phi 1, phi 2, phi n are not assumed to be solutions of any homogeneous linear equation. Can you still say that phi 1, phi 2, phi n are linearly dependent? The answer to this is in general no. But we have seen that if there is an n minus 1 by n minus 1, that is some for phi 1, phi 2, phi n minus 1 say, that is for n minus 1 of this set of functions of this collection of n functions, the Wronskian is not equal to 0, okay, at every point. Then you can say that the Wronskian vanishing identically of phi 1, phi 2, phi n implies the functions are linearly dependent. That's what we have proved. Now we go one step further. We say that if the Wronskian is identically equal to 0, we cannot say that on the whole interval it is linearly dependent. But what you can say is that there is some subinterval on which these functions are linearly dependent. Now this can be proved using induction. So I'll just write down the statement of the theorem. The proof is given in the book, so you will do it. Be any n functions continuous together n minus 1 derivatives let the Wronskian of be identically equal to 0 1 2. Then there exists a subinterval over which now this we have seen in the example. In the example of f and g that we have constructed, we have seen that f and g are linearly dependent on the interval 0 to minus 1 to 0, as well as it is linearly dependent on the interval 0 to 1 separately. But together on the whole interval minus 1 to 1, these two functions are linearly independent. Okay, in spite of the fact that the Wronskian is 0. So what you have is WFG identically equal to 0. However, so this example gives insight into this. Now the proof of this is done through induction. So you look into the book, proof by I leave it there. So it would be nice if you just look into the proof of this theorem. Now we make use of the power of this Wronskian determinant to study this problem further. See, what we do is now from linearly independent functions okay, can you go to the differential equation whose solution are or whose basis whose solutions have these functions as a basis. I hope you get the problem. The problem is this. Are smooth, sufficiently smooth functions. T2. That means n derivatives are continuous. And you have W of is not equal to 0 for every t belonging to that it vanishes nowhere. Okay? Then what you do, what you prove is there exists an nth order homogeneous linear equation uniquely determined whose solutions space is spanned by So what we have is that we are assuming phi 1, phi 2, phi n are smooth functions, and the Wronskian is vanishing nowhere on the interval t1 to t2, and there exists, then what you see, you go back to the equation, or you prove that there exists a uniquely determined nth order linear homogeneous equation for which the solution space is spanned by these functions. So let me try to prove this theorem. Okay. So the next theorem is, I will write it down. N times continuously differentiable over T1, T2 that is the interval, and let that is the solution. Then there exists a unique normalized homogeneous equation of order n having then this forms a basis for the solution space. Try to prove this. So our job is essentially very fascinating because we are getting a differential equation which are satisfied by this set of functions. Now, before we, okay. So define this is an n plus first order Wronskian phi. You know that this vanishes nowhere, therefore I can divide by that. What about this? This will give you an nth order linear homogeneous equation. So note that this is an n by n determinant is a homogeneous nth order linear ODE with the leading coefficient this is an nth order Wronskian. And you know that this is not equal to 0 anywhere on the interval, therefore you can divide by that. Therefore, this is a normalized equation. Now you look at this equation Lx equal to 4. You look at this equation, now you see that phi 1, phi 2, phi n are solutions of this. That is because you write down the n plus first column and replace it by phi 1, phi 2, etc. phi n. Then what happens? For each one of this, you will see that the n plus first column is identical with the ith column, say. Then the determinant is 0. So Lx equal to 0 for in short, phi 1, phi 2, phi n are solutions of this equation. Okay, so these are solutions of this. So what you get is L that's how you construct it. I mean, it's very simple. It's a simple work. How to construct such a differential equation provided the given condition is true. Now what happens is that, so on whatever interval on which phi 1, phi 2, etc., phi n is having this property, you can construct a homogeneous linear differential equation satisfied by this phi 1, phi 2, etc., phi n. That is possible. Now what we want to assert is that there exists only one such equation. How do you prove that? Suppose there are L1 and L2 are two such differential operators. Then you define L1 minus L2. Okay, then what do you have? You know that both L1 and L2 have their leading coefficient equal to 1. That is, they both are normalized. Therefore, when you take the difference, you see that M is a differential expression of at most order n minus 1, because the leading term will go away. And what you observe is that equal to 0, which is linear, homogeneous, and is of order less than or equal to n minus 1, and these are n solutions. Okay, and then what do you infer? Then equation such that these are linearly independent. But you know that for a linear homogeneous differential equation of order n minus 1, you cannot have n solutions which are linearly independent. In fact, every n solution of an n minus first order linear homogeneous linear differential equation is linearly dependent. This is a conversion. Which implies L1 is identically equal to L2. Or so that's the here. Now let us look at an example. You just actually go for the construction in the case of a specific example. So we'll take up a specific example. The specific example is this. Yeah. On the interval minus infinity to plus infinity, look at these functions. Take phi 1 t equal to sin t, phi 2 t equal to cos t. Now they are linearly independent. Independent. That's quite easy to do because, yeah, you can show that there exists no constants C1, C2 or C1 phi 1 plus C2 phi 2 equal to 0 if and only if C1 and C2 are 0. So that is quite easy to prove. It's not difficult at all. Now what do you do? We want to construct the differential equation. How do you construct the differential equation? You take Lx identically equal to, okay, what is the Wronskian of phi 1 and phi 2? This is equal to okay. So let me change slightly and just interchange the role of phi 1. Right here cos t. This is to get this equal to. Just a matter of definition. It does not matter really, but Now this is equal to 1, not equal to 0. So you have, now you write Lx equal to W what is this? Determinant of minus sin t cos t x derivative second derivative. Okay. So if you expand this about this column, you end up with this equation. Let's check whether you get this. Therefore, the corresponding equation is Lx equal to 0. You can easily check that both cos t and sin t are solutions of the equation Lx equal to 0. So that's how you construct the equation. Now we look at one basic structure of this Wt. Okay. So the next theorem is something more incisively about this function phi 1, phi 2. Sorry, the wrong scheme. So therefore, this is a sure way of constructing a differential, homogeneous linear differential equation, provided the given functions are having the property that W of phi 1, phi 2, phi n is not equal to 0 anywhere on the interval. Then only you can divide it by that. So that is the reason. Okay, so let us do the main, one of the nice results of this. So the next theorem is phi n be any fundamental set of minus I equal to, this is the definition of this, equal to 0 on the interval and we are assuming it's a fundamental set of solutions. It's a linearly independent set of solutions. Set That's the definition. T naught is some point in the interval T1, T2. Exponential P1 now this is an important identity. Now before we prove this remark, where of course P1 is given from here, it depends only on P. Yeah. You want to make some remarks. See, it also tells you that Wt does not depend on the particular fundamental set of solutions that you choose. Okay? Right? So, for all fundamental set of solutions, you see that it is essentially the same. So, this is something like an invariant that you have. Say, if you use, except for this Wt naught, which is the value of Wt at t equal to t naught. A second inference that you can make from here is that if for some t naught, Wt naught is equal to 0, then Wt equal to 0 for every t. Okay? Because this part is never 0. This is, if this is 0 for some t naught, then Wt is identically 0. Okay? So, that is some inference that you make about Wt. Okay. So, let me the value of is essentially of the particular fundamental set of solutions. It only depends on Wt naught is the only thing. That is why it is called essentially independent of the particular fundamental set of solutions. For each fundamental set of solution, you may have a particular value for Wt naught. But for all of them, they are different from 0. So, one is just a scalar multiple of the other. That is the only difference. So, essentially other properties are all completely with that. That is because you see that no matter what fundamental set of solutions you start with for this equation, you always end up with the you know, it's the same equation that all these linearly independent functions, that's the reason for it. So, this is something characteristically associated with this differential expression, and you can see that it comes from P1 tau, except for a multiplying constant which may vary. Okay, right. So, we will prove this theorem. So consider Lx, consider and since mx equal to 0 has and m is generated by 5152 and m is generated by m is identically equal to, so it is given m is identically equal to n. So there is only one such equation for which this could be a fundamental set of solutions under these circumstances. I mean a normalized equation. Now what you do is you equate the coefficient of x derivative on both sides. For L it is P1, okay, sorry, the n minus first derivative, okay. So equating the coefficients of on either side, that of L, we get P1, this is equal to minus 1 upon Wp. I'll write down the determinant. Determinant is phi n derivative and so on. You get phi n minus 2 and then look at the last row. The last row is going to be phi 1, okay, this one, n minus 1. So what one does is compare the coefficients on either side. So this is what you obtain. Okay, right. And that's not difficult to see, because what you do is you write down that matrix. Okay, so you have this particular matrix. Okay, I will write it this way. So you have W, what is it? This is equal to 1 upon W sorry, this is this. Sorry, n minus 1 is missing here. Okay, so you have phi 1 this is an n plus 1 by n plus 1 determinant that you have. Now you are taking the coefficient of this. So what do? You strike this row and strike this column, and then you get this matrix, and that matrix will come here, and you take the determinant of that multiplied by x to the power n minus 1, and you have to divide by Wt, and you will see that there will be a minus sign coming along with that, and when you compare with this, the x to the power, the n minus first, the coefficient of the n minus first derivative of x, you will get what? You will get P1. Okay, so it is from that you get this result. So you just work it out or verify. And then of course generalize it. That's the best way to see this. Okay. So once you get that, it is so. Now what we have is P1 is this one. Okay. Now let us compute this, what this is. Here you will see that this is not the n minus first, the row corresponding to the n minus first derivative is not appearing here. Okay. So what one does is, now we try to differentiate Wt. Okay. Compute W prime. How do you see? Incidentally, how do you get the derivatives? Derivative of a determinant. Okay, you get when you differentiate it, you see that they are product of terms. Suppose you take something like A11, A12, A13, what do you get? If you differentiate this, there will be a different terms involving the derivative of this, terms involving the derivative of this, terms involving the derivative of this. So if you write it up, eventually this is what you get. You can see that the derivative that you end up with is the following. Okay, row wise differentiated. Okay, where is that? You have this is the derivative of if you differentiate it, the first term will be all other terms remain the same, but the first row will be differentiated. The second term will be, the second row will be differentiated and all others will remain the same, and so on. So you get this is equal to, this term is phi 1 derivative, phi 2 derivative, etc. Phi n derivative, phi 1 two rows are identical. Then you have n minus first derivative plus n minus 2 other terms. Plus the last term phi 1 n minus 2 derivative, then you have phi 1 nth derivative, except for this particular portion, all other determinants, subdeterminants appearing in these terms have one row identical, therefore they are all 0. So you are left, and what is this? This is essentially what we have computed here, the coefficient of the term related to P. So from this equating, so all these terms are 0. They do not make any contribution. It is left to this. Therefore you are left with that gives W and consequently you get Wt equal to therefore you get So it satisfies a first order equation. So what you have is that w prime t plus equal to 0. Now you integrate. I mean, it's a first order equation. It's a very simple first order equation. And the solution is given by wt equal to minus, sorry, not minus, integral so that gives the. Now one of the consequences is that phi t is identically 0 if and only if phi t naught, okay, sorry, wt this we have seen the fundamental set of solutions of the differential equation, nth order homogeneous linear differential equation that we have taken up has this property that they are linearly independent if and only if they are linearly independent at a some t naught. Okay, so either they vanish everywhere or they vanish nowhere. Okay, so that completes the talk. Thank you.